A Brief History of Time, Chapter 1, Part 5. It turns out to be very difficult to devise a theory that describes the universe all in one go. Instead, we break the problem up into bits and invent a number of partial theories. Each of these partial theories describes and predicts a certain limited class of observations, neglecting the effects of other quantities or representing them by simple sets of numbers. It may be that this approach is completely wrong. If everything in the universe depends on everything else in fundamental way, it might be impossible to get close to a full solution by investigating the parts of problems in isolation. Nevertheless, it is certainly the way that we have made progress in the past. The classic example again is the Newtonian theory of gravity, which tells us that the gravitational force between two bodies depends on one another, associated with each body, its mass, but is otherwise independent of what the bodies are made of. Thus, one does not need to have a theory of the structure and the constitution of the sun and the planets in order to calculate their orbits. Today, scientists describe the universe in terms of two basic partial theories, the general theory of relativity and the quantum mechanics. They are the great intellectual achievements of the first half of this century. The general theory of relativity describes the force of gravity in the large-scale structure of the universe, that is, the structure of scales from only a few miles to as large as a million, which is one with 24 zeros after it, miles, the size of the observable universe. Quantum mechanics, on the other hand, deals with phenomena on extremely small scales, such as million of a millionth of 1 inch. Unfortunately, however, these two theories are known to be inconsistent with each other. They cannot be both correct. One of the major endeavors in physics today and the major theme of this book is the search for a new theory that will incorporate them both, a quantum theory of gravity. We do not yet have such a theory, and we may still be a long way from having one, but we do already know many of the properties that it must have, and we shall see in later chapters that we already know a fair amount of the predictions a quantum theory of gravity must make. Now, if you believe that the universe is not arbitrary but is governed by the definite laws, you ultimately have to combine the partial theories into a complete undefined theory that will describe everything in the universe. But there is a fundamental paradox in the search for such a complete undefined theory. The idea about scientific theories outlined above assume we are rational beings who are free to observe the universe as we want and to draw logical deductions from what we see. In such a scheme, it is reasonable to suppose that we might progress ever closer towards the laws that govern our universe. Yet, if there is really a complete unified theory, it would be presumably determine our actions, and so the theory itself would determine the outcome of the search for it. And why should I determine that we come to the right conclusion for evidence might not equally well determine that we draw the wrong conclusion or no conclusion at all. The only answer that I can give to this problem is based on Darwin's principle of natural selection. The idea is that any population or self-reproducing organism, there will be variation in genetic material and upbringing that different individuals have. These differences will mean that some individuals are better able than others to draw right conclusions about the world around them and to act accordingly. These individuals will be more likely to survive and reproduce, and so their pattern of behavior and thought will come to dominate. It has certainly been true in the past that what we call intelligence and scientific discovery have conveyed a survival advantage. It is not so clear that this is still the case. Our scientific discoveries may well destroy us all, and even if they don't, a complete unified theory may not make much difference to our chances of survival. However, provided the universe has evolved in the regular way, we might expect that the reasoning of abilities that natural selection has given us would be valid also in our search for a complete unified theory, and so would not lead us to any wrong conclusions. Because the partial theories that we already have are sufficient to make accurate predictions in all but the most extreme situation, the search for ultimate theory of universe seems difficult to justify on practical grounds. It's worth noting thought that similar arguments could have been used against both relativity and quantum mechanics, and these theories given as both nuclear energy and the microelectronic solution. The discovery of a complete unified theory therefore may not aid the survival of a species. It may not even affect our lifestyle, but ever since the dawn of civilization, people have not been content to see events as unconnected and inexpensible. They have craved an understanding of underlying order in the world. Today we still yearn to know why we are here and where we came from. Humanity's deepest desire for knowledge is justification enough for our continuing quest, and our goal is nothing less than a complete description of the universe we live in.